Hello maths fans, we're going to look at percentage error. This is in the topic of rounding, and we should already know about lower bounds, upper bounds and error intervals. So the sort of minimum that a value could be before it was rounded and the maximum it could be before it was rounded. Percentage error then. So whenever we measure a quantity, there is almost always a difference between our measurement and the actual value. So the difference between our sort of estimate or our approximate answer and the actual value is the error. So the size of that error is, whether it's too high or too low, it's called the absolute error. And it's an absolute value because it's always just a positive number. So if it is 3 too low or 3 too high, we just give it a value of 3. Let's have a look at the formula for this. So the actual or exact value we could call VE for exact, and the approximate value we could call VA for approximate. Then the absolute error is the approximate value, subtract the exact value, and then make it positive. That's what these two lines, these vertical lines here, just mean the modulus, which is to make something positive, pretty much. Let's look at that in an example. It should be pretty clear. I round 933 to the nearest 100, and I get 900. So if I want to know my absolute error, very simply, I just take one away from the other and make it positive. So 900 minus 933 would be negative 33. We make that positive, 33. So pretty obvious, the error here, the absolute error, is 33. I'm 33 out. Now, we often want to express that as a percentage of the exact value. Now that part there is quite crucial because people do make the mistake of dividing by the wrong thing. So, of the exact value, it's a percentage of the exact value. Not a percentage of the rounded value, a percentage of the exact value. So when we're finding the percentage error, we take the absolute error, that's the top part, that's that calculation we already did. Looks complicated, just find the difference. Find the difference between the rounded value and the exact value, and then divide it by the exact value on the bottom there. Okay? And change it to percentage, times by 100. So you could use this formula, or you can say it's the absolute error divided by the exact value times 100. So in our case, we've got 33 is our absolute error, divided by the exact value, 933, and then change it to a percentage times by 100. In this case, it would be 3.54%. So that is the calculation that we do to find the percentage error. We find the absolute error by subtracting, divide it by the exact value, times by 100. Here's one for you to try. So we've rounded the length of a bridge to 43, which was 43.9 meters to 40 meters. So I want to know the absolute error and the percentage error. Pause it, have a go at it now, and then I'll share the answer. And here is the answer. So the absolute error is just going to be subtract them. We get 3.9 meters, make it positive. The percentage error is 3.9 out of the exact value, divide by the exact value there, times 100. And in this case, 8.88%. Which is 3 significant figures. So yeah, that's some sort of fairly straightforward example. Now we're going to look at a slightly more complicated value example where we've got values that are rounded, then an operation was performed, and now we want to find the percentage error, the maximum percentage error. And there's a little bit more to this one. So we've got a square which is roughly 22 centimeters. That's been rounded to the nearest centimeter. So an estimate for the area of the square would be 22 times 22, because area of a square is length times itself, length squared, and we get 484 centimeters squared. That's an estimate for the area. Now find the boundary values for the area of the square. Well, it's not just find the upper and lower bound for this number. What you've got to do is you've got to find the upper and lower bound for our initial rounded value. So the side length was going to be between 21.5 and 22.5. If it's rounded to the nearest centimetre, that's the minimum it could have been, that's the maximum. Okay? Now that we know that that's the minimum side length and the maximum side length, let's work out what the area would be if it was the minimum. And that would be 21.5 times 21.5, 462.25. And then we work out what the area would be if we had the maximum lengths for the side of the square. So if it was the maximum, the upper bound would be 22.5 times 22.5, 506.25. So those are the limits, the upper bound and the lower bound, for the area of this square. The last one here says, hence find the maximum percentage error in the estimate. So we want to find, we don't have an exact value here. We don't know what the exact length of this square was, but we know what the minimum would have been, and we know what the maximum would have been. So we're going to find the maximum percentage error. So what we're going to do is, well, as it says there, we don't know the exact value, so we need to state what the maximum is. To do this, we're going to check both the upper and the lower bound to see which gives us the biggest percentage error. So, if we use the lower bound, if we use that value, then our percentage error, we're going to do the rounded value minus that lower bound and divide it by that lower bound. We're going to assume this is the exact value. We're going to see what would happen if this was the exact value. Okay? So, we subtract, work that out, divide it by our minimum exact value. And so, if the square had those minimum side lengths, the percentage error would be 4.71%. Now we're going to do the same for if the square had those maximum lengths. So if it was 22.5. So there is our upper bound. We'll subtract it from the estimate for the area. Then we'll do that as a percentage of the exact value. Well, we don't have an exact value, but this is what we're going to say. What if this was the exact value? If this was the exact value, the percentage error would be 4.40%. Now the question said, hence find the maximum percentage error. Well, the maximum percentage error clearly is 4.71%. Not this one. So I'd be further out on my estimate if it was the minimum length, the lower bound that we used. So that percentage there is the maximum percentage error. Hope that makes some sense. Right, here's one for you to try. Have a good read of this and then have a go at it. I'll just point out a couple of things before you pause the video. So it says a builder has two steel bars, one of 6.0 meters, one of 8.5 meters, and they've been rounded to the nearest 0.1 meters, nearest 10 centimeters. Hence, she estimates the total length of the two bars to be 14.5 meters. Yes, the builder is a woman. That's allowed nowadays. Don't be sexist. Now it says, what are the boundary values for the total length of the poles? So you've got to find the upper bound and lower bound here, upper bound, lower bound here, and then work out what is the minimum that the two poles together would be, and what's the maximum that the two poles together would be. Then you're going to change that and work out a percentage error. Pause it now, give it a go. Okay, here are some answers. So, lower bound for the first one is going to be 5.95 meters. Lower bound for the other pole is going to be 8.45 meters. So the smallest that they could both be together will be that lower bound, add that lower bound. And we get 14.4 meters. Similarly with the upper, we get 6.05 plus 8.55. And when we add those together, we get 14.6 meters. So that's the upper bound for the maximum that those two poles next to each other could be. The the maximum percentage error in that estimate, well, we've got to work out the percentage error when we use the lower bound. So when we use the lower bound, well, you do 14.5 minus 14.4 divided by what we're assuming to be the exact value. We're going to say what if it was the minimum, times it by 100, and we get 0.694%. Then we do this calculation with the upper bound, and we get 0.685, and therefore 0.694% is the maximum percentage error. Okay, hope that makes sense. Go and do some practice, a few questions like this, so you get used to it. Thanks for watching.